In this module, you will learn about Pascal's law and hydraulic machines. Consider a very small element of fluid in the form of a right-angled prism, A, B, C, D, E, F, inside a fluid at rest. As the element is very small, every part of it is considered at the same depth, and hence the effect of gravity is the same at all points of the fluid element. We know that the force exerted by the rest of the fluid on the element is normal to the surface. Let FA, FB and FC be the normal forces acting on the three rectangular surfaces of the prismatic element. AA, AB and AC represent the areas of the faces BEFC, ADFC and ADEB of the element respectively. PA, PB and PC represent the pressures acting on the areas AA, AB and AC. Geometrically, in the right-angled triangle ABC, BC is equal to AC cosine theta and AB is equal to AC sine theta. The forces shown are normal to the respective areas that include the sides. Thus, we have FB sine theta is equal to FC and FB cosine theta is equal to FA. Let us call this equation 1. As the thickness of the prismatic element FC is constant, the areas of the three sides of the prism can be expressed in terms of the trigonometric ratios as shown for the forces given by equation 2, which is AB sine theta is equal to AC and AB cosine theta is equal to AA. Dividing equation 1 by equation 2, we get FB divided by AB is equal to FC divided by AC, which is equal to FA divided by AA. However, the ratio of force to area is equal to pressure. Thus, PA is equal to PB, which is equal to PC. Hence, we can conclude that the force against any area within a fluid at rest and under pressure is normal to the area irrespective of the orientation of the area. The pressure exerted at a point by a fluid at rest is equal in all directions. Hence, pressure is a scalar even though it is in the ratio of force, which is in general a vector to area. This is what Blaise Pascal postulated as Pascal's law. Pascal's law states that when external pressure is applied at a point in a fluid contained in a vessel, it is transmitted undiminished and equally in all directions. Let us understand it in detail using an activity. Consider a spherical vessel containing 4 cylindrical tubes A, B, C and D of area of cross-section A, 2A, 3A and 4A. Each of these openings is fitted with an airtight piston. Let piston A be pushed with a force F. Then the pressure on the piston is F by A. Pistons B, C and D move out due to this pressure. However, pistons B, C and D can be held in their position only when the forces applied on them, that is, FB, FC and FD are equal to 2F, 3F and 4F respectively. Then the pressure acting at B, C and D is 2F by 2A, 3F by 3A and 4F by 4A respectively, where each is equal to F by A. This experiment demonstrates that the pressure is transmitted undiminished in all the directions, which proves Pascal's law. A number of devices such as a hydraulic lift, hydraulic press and hydraulic brakes work according to this law. Let us look at each of them in detail. A hydraulic lift is used to lift or support heavy objects. It consists of two cylinders fitted with airtight pistons of varying cross-sectional areas. The two cylinders are connected to each other with a horizontal pipe, where the container is filled with an incompressible liquid. The load to be lifted is placed on the piston of larger cross-sectional area. A2. Let a downward force F1 be applied on the smaller piston A1. According to Pascal's law, this pressure F1 divided by A1 is transmitted equally to the piston, where A1 is the area of cross-section of the smaller piston. As this pressure is transmitted equally to the large piston, the upward force F2 acting on the load is equal to the product of the pressure and area of cross-section of the larger piston A2. As A2 is greater than A1, we have F2 greater than F1. Thus, with a very small force, heavy objects can be lifted using a hydraulic lift. The work done by the smaller force is equal to the work done by the larger force, as the displacement of the smaller piston is greater than that of the larger one. Here, the force F1 applied on the smaller piston is called the effort, and F2, the force required to lift the heavy object, is called the load. By definition, the mechanical advantage of a machine is the ratio of load F2 to effort F1. Substituting F2 with PA2 and F1 with PA1, we get the mechanical advantage as A2 by A1. Hence, we can write the mechanical advantage of a hydraulic lift as the ratio of the cross-sectional area of a larger piston to that of a smaller piston. Let us now study a hydraulic press. A hydraulic press is a mechanical machine used to lift or compress large loads. The schematic representation of a hydraulic press that works on force applied manually is as shown. In this machine, a smaller force applied on a column of liquid is converted into a much larger force acting on the load placed on another column of the liquid, connected to the first column. A hydraulic press consists of two cylinders, C1 and C2, fitted with pistons P1 and P2, and valves V1 and V2 connected with tube T1. Tube T2 connects the cylinder C2 with a water reservoir through a release valve, RV. Piston P2 is a platform at the top of which the substance to be compressed is placed. Piston P1 is raised upwards by the application of force F at the handle edge of the lever. Upon the action of the handle, the valve V1 opens. The water from the reservoir is sucked into the cylinder C1. During this process, valve V2 remains closed. When piston P1 is pressed down, valve V2 is opened. Valve V1 is closed and the water is pushed from cylinder C1 to cylinder C2 through T1. Due to water pressure, piston P2 moves up, compressing the load between the platform P and the rigid ceiling. To release the pressed substance, the release valve RV is opened to allow the water back to the reservoir. Another device that conforms to Pascal's law is a hydraulic brake used in automotives. A hydraulic brake consists of a master cylinder M, filled with brake oil and provided with an airtight frictionless piston P. Through a lever system, the piston is connected to the brake pedal F. Through a tube T, the master cylinder is connected to a wheel cylinder C, consisting of two pistons P1 and P2, which are connected to brake shoes S1 and S2. The same system is connected to the other wheels of a vehicle. When the brake pedal is pressed, the lever system operates, transferring the force to the piston P. The piston P is pushed inward, increasing the pressure in the master cylinder. According to Pascal's law, this pressure is transmitted to pistons P1 and P2 in the wheel cylinder. These pistons force the brake shoes S1 and S2 to move away from each other, which in turn press against the inner rim of the wheel. Hence, the brake works and retards the motion of the wheel. When the pressure is released, the brake shoes return to their normal positions with the help of a spring mechanism. You have now reached the end of this module. In this module, you learned that Pascal's law states that when external pressure is applied at a point in a fluid contained in a vessel, it is transmitted undiminished and equally in all directions. A number of devices such as a hydraulic lift, hydraulic press, and hydraulic brakes work according to Pascal's law.